Good to go.
Okay, thank you very much. Corrosion could easily be a 2-semester college course. We're going to cram it into about 45 minutes here. So obviously, this is going to be a very quick overview. And in discussion with Randy, I'm going to focus on just 2 areas of corrosion: straight current corrosion and shore power issues with corrosion. Just an outline of what we'll be talking about: corrosion theory. Unfortunately, you can't understand corrosion with understanding a little bit of electricity and chemistry. Now, I've used 3 sources here. My primary source is ABYC's Marine Corrosion Certification course. And if anybody's taken this in the past, this is a brand new book. I picked it up just from the printers a couple of weeks ago, and it's a much better course than it used to be. And thanks to ABYC, they allowed me to use some of the slides in my presentation from this book. Some of the reference material that I've used, and you've probably seen all these: Boat Owner's Guide to Corrosion, Metal Corrosion in Boats, and then Nigel Calder's Boat Owner's Handbook, I guess, manual. The interesting thing is, when you read any 3 of these or 4 references, the same subject will be presented totally differently, using different terminology and different theories. So some of you may not agree with some of the things I said, because I'm following ABYC's theories, but it's all close, and when you get to the details, it's basically the same, but it's always presented in many different ways. So we'll touch on very briefly 2 corrosion types, and primarily just those 2 that I mentioned before, and again, mitigation of those 2 types, and then a corrosion survey. Does anybody here do formal corrosion surveys? Okay, good, good. And thanks again to ABYC for allowing me to use some of their material. So definition of corrosion: first of all, electrochemical reaction. That's the key. It's electricity and chemistry together. Now there's many different definitions of corrosion. Those 4 references I mentioned, they all have different definitions. But one thing is in common to all of them: electricity is either produced or consumed. Produced would be the typical galvanic corrosion. Consumed would be straight current corrosion. Corrosion happens at the atomic level, so we got to look at atoms. Going back to high school chemistry now and college chemistry, you all remember that atoms are formed by, are composed of nucleus and the outer shell of electrons. The nucleus is protons and neutrons. The number of protons dictates the atomic number of an atom, and the number of protons, positive charges, always equal the number of electrons in a stable atom. It's the outer shell of electrons, and we're going to keep coming back to electrons all the time in this presentation. It's all about electrons. And so it's the outer shell that wants to be stable. The outer shell, if it's, will always want to have 8 electrons in the outer or valence shell. If there's only one shell of electrons, it's going to be the inner, same as the inner shell, there'll be 2. Again, you'll see that again and again. When the outer shell of the valence shell is full, the atom's stable. It's the atom's tendency to gain or lose electrons determines whether it's susceptible to corrosion. Here's hydrogen, oxygen, and then the 2 combine into a molecule of water. For instance, when you start talking about electrons, hydrogen has 1 proton, its atomic number is 1, and so it has 1 electron. Well, atomic theory says that if you have 1 shell of electrons, you want 2 electrons in it for the atom to be stable. So 2 hydrogen atoms come together to form a hydrogen molecule, and they share, each shares its 1 electron with the other, so they have, each has 2 electrons in its valence shell. Oxygen has 6 electrons in the outer shell. Its number is 8 protons. So it's looking to pick up 2 electrons from some other element. So you'll get oxygen combining with oxygen, for a molecule of oxygen, again having 8 electrons in the outer shell. And a molecule of water will, oxygen will share its electrons with hydrogen. Now what's really important here, the previous slide was called covalent bonding. This is a critical slide to understand corrosion. Metal atoms are arranged in a lattice. The electrons are so weakly bound to the metal atoms that they freely roam across the entire metal. Having lost their outer shell of electrons, the metal atoms becomes positive ions in just a swarm of electrons. This type of chemical bonding gives metals their unique properties such as conductivity, ductility, and corrosion. The electrons in metals are very loosely held. That's why they will corrode, that's why they conduct electricity. Okay, electron flow theory. This is counter to what most of us learned, and we still learn, in high school and college, where we learned that electrons always flowed from positive to negative. In electron flow theory, electrons flow in metals always from negative, the anode, toward the more positive cathode. Notice it's more positive. It could still be negative, but it is less negative or more positive. So keep this in mind. And anything I've highlighted in yellow is a key point to understand in understanding corrosion. Electrons flow in metal, and they flow from negative to more positive. Okay. Next concept is ionization. It's a process by which atoms or molecules acquire positive or negative charge by losing or gaining electrons. Ions can, and this is key, ions can only form and travel in electrolytes. Okay, that's fundamental to corrosion. Now, I handed out the galvanic series of metals. We'll be talking about some different metals here, and you can refer to that sheet. Couple things to know about this is that this galvanic series is for seawater only, flowing at a fairly respectable 2 to 4 knots, and it's relative to the silver chloride reference cell. If you look at that table, and it's hard to read up here, but that's why I handed these out. What's the maximum differential? What's the differential from one end of that table to the other? It's roughly 1900 millivolts, less than 2 volts. Okay, that's what drives galvanic corrosion. It's not much voltage, okay? That will become critical when we start talking about straight current corrosion. Okay, we've got 3 different types of electrochemical corrosion. Now, there's other kinds of corrosion like mechanically assisted impingement corrosion, cavitation corrosion. They can be related to galvanic corrosion because of the passivity, how galvanic corrosion affects the outer coating of some metals will allow these mechanically assisted corrosions to take place. But we're going to talk about galvanic or electrochemical corrosion only. First of all, simple electrochemical corrosion, single metal rusting. The iron hull, steel hull of a ship will corrode on its own. That's single metal corrosion. Now, the process of galvanic corrosion is still taking place, and that's what causes the rust, but it's still one single metal. The second type of electrochemical corrosion is galvanic corrosion. That's two separate metals or alloys. That's when we get into galvanic corrosion as opposed to single metal corrosion. So we're going to talk about that and specifically how a shore power system can aggravate and cause that problem. Then the third type of electrochemical corrosion is electrolytic corrosion or stray current corrosion. So we're going to focus on the last two, galvanic and electrolytic corrosion. Now, galvanic corrosion, again, two separate metals. We're talking about two metals or two alloys. There's four things you have to have for galvanic corrosion. You have to have an anode, you have to have an electrode, you have to have a common electrolyte that these two metals or alloys are in, and you have to have a metallic path. The metallic path is for the electrons to flow in. Go back to your ion flow or electron flow theory. That's why you need the metallic path, because we're going to be talking about electrons flowing in a metallic path. Here's the bottom line. This is the nitty-gritty of galvanic corrosion. So when you're trying to do a corrosion survey or trying to understand corrosion, follow the electrons. The first thing I do is try to figure out where are electrons going, because that's the simplest thing to see when you're looking at a boat with a galvanic corrosion issue. We'll start at the anode. Electrons. What did we say about electrons? They go from negative to positive, or from negative to less negative. Okay, so in this case, they're going to go from zinc, and you'll see on that sheet that zinc has a potential of roughly minus 980 millivolts. The electrons will flow from that to the more positive or less negative. In this case, silicon bronze, negative 260 millivolts. Electrons flow from the negative to the positive. So when the electrons on the surface of the zinc anode leave the anode, those electrons are coming from that slurry of electrons in this metallic lattice of atoms. So those electrons leave the anode, leaving behind positive ions. And that's the little red pluses that you see jumping off of the anode. Those are positive metal ions jumping off of the anode. That, by definition, is rust. Those are rust particles. When they combine in the electrolyte with hydroxide, they become metal ions. We call it rust. So we follow the electrons from the anode over to the cathode. What's happening in the cathode? The electrons are flooding the cathode. The electrons that are coming into the cathode via the wire metallic path are pushing other electrons out into the electrolyte. The important part there is there's no net change in charge or particles in the cathode. The electrons that are jumping off of the cathode into the electrolyte are being replaced immediately by the electrons flowing into it from the anode. So that's protected metal. The cathode is the protected metal. That's why we can protect our bronze prop stainless shafts, because the anode is providing the electrons. Now, what's happening in the electrolyte is that the positive ions are jumping off the anode, are combining with hydroxides ions in the electrolyte, forming rust. And the electrons that are coming off the cathode are combining with negative ions, joining with probably hydrogen to make a hydrogen molecule, for instance. And that's why sometimes you'll see a cathode bubbling. That's hydrogen being bubbled off the cathode. It can also, that hydrogen can also enter the metal and cause hydrogen embrittlement and some other things. But basically, the negatively charged ions coming off the cathode combined with ions in the electrolyte. We'll see the same thing, the same process again and again in this presentation. Now, very briefly, we're not going to dwell on this because this isn't the type of the corrosion we're talking about, but this is the simple or single metal corrosion. The anodes and the process is identical to what we just talked about. The anodes and cathodes develop on the surface of the same metal because metals are not pure. So the metals we see in the industry are not pure. They'll have anodic and cathodic surface areas. So those are the anodes and cathodes. The moist air on the hull of the ship becomes a common electrolyte. Not a real good electrolyte, moist air. That's why simple or single metal corrosion isn't real fast. And then the metal itself becomes the metallic path for the electrons to move. The types of single metal electrochemical corrosion: pitting, dealloying, crevice corrosion, poultice, erosion, microbial corrosion, well decay, and I've got a couple examples here. Here's the hull of a ship. Simple corrosion, carbon or mild steel, all one metal, but it's still corroding because of the anodic and cathodic areas on the surface of the metal. Iron oxide, which is the rust, has come off of the anode, is not well adhered to the surface of the steel, right? So it flakes off, exposing more steel, and the process just continues and continues. An effective coating is probably the best way to protect a mild steel. Typical of this would be pitting corrosion. Again, single metal electrochemical corrosion, where you've got a cathodic surface and you break the passivated cathodic surface coating, exposing maybe some anode underneath, some anodic material on the surface. Remember, stainless steel is stainless because of this passivated coating on it. Aluminum doesn't rust because of the coating oxide, aluminum oxide on the surface. Well, if you break that passivated stainless steel surface or break that aluminum oxide surface, those materials will oxidize. And typical pitting corrosion would be typical of that. De-zincification in this case, or dealloying, is another type of single metal, can be another type of single metal corrosion. In this case, you've got bronze, probably manganese bronze nuts. Manganese isn't a bronze, it's a brass made of copper and zinc. Well, when you have copper and zinc together, you got two metals. One's zinc is anodic to copper. So in the proper environment with an electrolyte, the zinc in the manganese bronze will sacrifice itself to the copper. Now, something interesting on this slide. Do you see anything else wrong with this slide as surveyors?
Nuts are on back.
The nuts are on backwards. Probably, according to most theory, those nuts are backwards, yeah. Okay, now we'll get into the details of galvanic corrosion, and then how does a shore power system aggravate or cause a galvanic corrosion? It's the most common corrosion in the industry. You see it everywhere. It's much faster than simple electrochemical corrosion. A mild steel plate will rust, but it will take a long time to be rust to a point where the structure of the mild steel is significantly deteriorated. So galvanic corrosion drives the process with some electrical potential, so it's much faster. Factors influencing the rate of galvanic corrosion, the big one is the galvanic voltage difference. If you take two metals, immerse them in an electrolyte, and connect them with a the metallic path. And the metal, one of the metals is on the top of that list I handed out, and one is on the bottom of the list I handed out. You've got almost 2 volts driving that galvanic cell. So it can go fairly fast. Now, make it straight current. We'll talk about that some more, and you could have a lot more than 2 volts going through there. The relative surface area, the anode cathode surface area will affect the rate of galvanic corrosion. Conductivity of the electrolyte. Salt water is a pretty good conductor compared to, say, fresh water. Water temperature, the higher the temperature, the more active the reaction. And the flow rate, the electrolyte flow rate. The more flow, the faster the galvanic corrosion rate could be. Here's a typical galvanic corrosion issue. You got a stainless steel, maybe aquamet shaft. It's got one zinc anode on it, and if you look close, you'll see where the second, there's a second anode has fallen off there, and the anode has disappeared from the rudder altogether. So, but you've got a stainless steel shaft, probably a bronze, manganese bronze propeller, a bronze rudder. You've got all the makings of an electrochemical cell. You've got anodes, cathodes, you've got the electrolyte as a salt water it's sitting in, and all this stuff is probably bonded together. So you've got a real good galvanic cell there. Here's another place where galvanic corrosion can be aggravated tremendously by shore power connection. Cathodic corrosion or overprotection, where you're driving the cell or you've got such a voltage differential that, remember I said on the cathode, the negative ions are jumping off the cathode as they're being replaced by new ions. Those ions combine with hydroxides in the water, creating hydrogen, which can affect the alkalinity, the pH of the water. So if you overprotect wood, and in a stagnant water environment especially, you'll get a strong alkaline mixture around the protected wood, the cathode, and that will start to eat up the fibers of the wood that hold, or the lignin in the wood that holds everything together, and you get fuzzy wood. Usually it'll be visible on the inside of the hull. You get fuzzy wood, or what's called wood burning. We'll talk a little bit more about that later. Okay, now those 2 galvanic issues. Again, if you've got the metal that you're talking about, or the anode and cathode are at the extreme ends of the galvanic series that I handed out, you could have almost 2 volts driving it. Well, in this case, there's a lot to this that we don't care about. What we're looking for is how a shore power system can set up a galvanic corrosion problem on your boat. So here's your boat over here. You've got a nice zinc anode, could be aluminum anode, but say it's a zinc anode, and your whole boat is bonded. It's all the metal is bonded together. Your propeller, your shaft, everything is all bonded together. So your boat's great. It's properly protected at cathodes and anodes. And here's the electrolyte that these 2 boats are sitting in. Well, if you look at a shore power system, your bonding system is tied into your grounding conductor, correct, as most boats are supposed to be, or all boats are supposed to be. That grounding conductor follows your shore power cord to the dock, and it follows this other guy's shore power cord to his bonding system. He's got no zinc. All of a sudden, you've got a galvanic cell set up between your zinc and his running gear. So this is a case of where a shore power system can aggravate a galvanic corrosion issue on your boat. Your boat can be properly wired with sacrificial anodes so that by itself it would have no problems at all, but the boat next to you could easily cause a problem. Yes?
And then that's why the anodes go off quickly because one is doing the other.
Yeah, think of a boat around in an Annapolis marina that's got 50 boats all tied into the same shore power system. So if half those boats, 50 boats, don't have enough zinc, or they didn't get replaced and they're worn, your boat could be anotic to all the other boats on the same system. More about that later. Let's talk about electrolytic or straight current corrosion now. It requires a power source, okay? And this is the most aggressive, rapid, and dangerous form of corrosion because the process is being driven by, could be quite a bit of power. An important thing to remember here is it's always the result of faulty wiring or faulty equipment. Something has been done wrong or something has failed in order to have straight current corrosion. Now, said at the bottom, it's not electrolysis. You still hear that all the time. One of these books actually shows a propeller, I think, a prop that has been eaten up by galvanic corrosion, and it calls it electrolysis. It's not electrolysis. So I'll define electrolysis. Chemical decomposition, that is separation of the elements, produced by passing DC current through an electrolyte, like seawater. It's also called dissociation, and there's the chemical, that is electrolysis. That's a chemical formula for electrolysis, breaking down of water into hydrogen and oxygen. Now, electrolysis can be a byproduct of straight current corrosion, but electrolysis is defined as what happens to the electrolyte. Corrosion is what happens to the metals. So when you see a prop or something eaten up by galvanic corrosion, it's not electrolysis. Where do we use electrolysis? It's used every day. Not removing hair, that's not really electrolysis. On submarines, that's how they make oxygen on submarines. They pass electrical current, which is unlimited on a nuclear power submarine, through water, breaks it into hydrogen, which they vent off, and oxygen to breathe on board the submarine. Okay, remember the galvanic corrosion quadrangle where you needed the four things? Same thing here. You need an anode, you need a cathode, you got the common electrolyte, but in addition to the metallic path, you've superimposed a power source. Still got to have the metallic path, but you've got a power source in the metallic path. That power source is typically your onboard batteries. What's the battery? 12 or 24 volts. So on that when we're talking about galvanic currents, remember we said you could have almost 2 volts DC driving galvanic corrosion. You could have 12 or 24 volts driving straight current corrosion. The process is the same. The process of the galvanic corrosion is the same. The deterioration of the anode, protection of the cathode, it's the same, but it's now being driven by 12 or 24 volts. Here's the typical scenario. You've got your positive lead from your battery has been taken off. So you've got a couple batteries, battery bank, and you've taken a battery out to replace it. You disconnect one of the leads, it drops into the bilge and comes in contact with a bronze through hull. So what's going on here? What's the anode? What's the cathode? How do we figure out, if we're doing a corrosion survey on this boat, how do we figure out what's happening and why? Follow the electrons. Always follow the electrons. Your through hull, bronze through hull, is now got a metallic path back to your positive terminal on your battery. Electrons will flow from less negative to more positive direction, always from negative to positive. And you can't get any more positive than that battery positive cell. So you're going to have electrons flowing from this through hull through the wire to the positive cell of the battery. As those electrons leave that bronze through hull, that kicks off those positive metal ions into the electrolyte, the seawater, and by definition, that's corrosion. And those, you'll start seeing, if there was no flowing water on this boat, you'll start seeing a little cloud, brown cloud of positive metal ions coming off this bronze through hull. Now, at the same time, the positive charge on this, the positive charges here, will tend to draw electrons from this negative cell through this metal path to your propeller, and these electrons will jump off the cathode, combine their ions, they'll come off as ions, electrons as ions, and combine with the hydroxides or oxides in the water. So you get hydrogen oxides and metal hydroxides in the electrolyte, but you get the flow of electrons through the metal, and then the ions will flow through the electrolyte. This is just like the anode and cathode that we saw, only this is being driven by 12 volts. Yes?
Years ago in Baltimore, I looked at a big sailboat that had sunk. And this is exactly what happened, what you're talking about. Of course, the zinc was gone.
Yeah.
And over the course of about 4 days, it ate the through hulls out of the boat.
Yeah.
And there was nothing left of it. And that's a bonding system. That's
Which,
why I've always been kind of against bonding system requiring people, because in this case,
yeah,
this boat would not have sunk
right.
without a bonding system.
ABYC.
Or somebody with sand and water coming out, but once they started going,
Oh, yeah. Yeah. ABYC does not require a bonding system on boats. There is they do recommend it, but there's a whole school of thought that says you don't want to bond everything together. For that's one of the reasons.
So
yes.
it would do the same thing if that wire was just hanging on the bilge board. Doesn't have to necessarily be touched.
Like that.
Oh, okay.
Yeah. This is probably more common, and the next slide is even more common. Yes.
Back on the slide there, please. When that occurs there or in the bilge, that would cause the ring around the through hull of discoloration too, right?
That, but you'll get the ring around, if you're overprotecting any metal, you'll get a discoloration around it from the hydrogen, from the hydroxides.
I had a situation where I was doing a boat and there was all around the metal objects, you know, through hull, trim tabs, everything. There was probably a ring around it. Halo. Come to find out, halo around it.
Yep.
Come to find out that this boat was sitting by two bubblers that were in the water, and all the cords were in the water.
Yeah. Yeah. Yeah, just plain galvanic corrosion can, if it's overprotected, you got too much zinc on the boat for the amount of protected metal, you can get some haloing. Usually it's not too dangerous, but it does deteriorate. It is very dangerous in a wood boat or an aluminum boat. Yeah. Overprotection in those two can be very dangerous. Same situation here, just the cable is dropped into, and this is more likely. The scenario just drops into the bilge water. You've got the same thing here, okay? You've got a bronze, copper battery clamp has dropped into the water. That becomes the anode, and you get exactly the same process. So what would you expect to see of that battery clamp after a day or two? When you discover what's going on and you pull that wire out, it's part gone. You got a little green mushy stub because that became the anode and it got sacrificed. Here's a more likely scenario. This is not unusual, and I've seen this a few times. Bilge pump wiring. Okay, right now we've got, this is wired properly. The float switch is in the positive lead, so you've only got power to the motor in that pump when that float switch comes on, right? What happens if you mount the float switch in the negative lead? Do you not have power all the time to that motor? And then the little seal starts to leak between the pump impeller and the motor, so that you've got electrolyte now touching in contact with the motor shaft, and you've got the metallic path, and you've got the electrolyte now because you've got bilge water, so you've got galvanic corrosion that's being driven by a 12-volt battery. That's not uncommon. When you start seeing what you think are stray current corrosion problems, that's one of the first things to check is your bilge pumps. How am I doing on time? Doing okay? Okay. Corrosion mitigation. Again, we're going to focus on those corrosion mitigation of those two types of corrosion, stray current and dockside galvanic corrosion issues. Mainly by design, it is how you handle those issues. Coatings a little bit, cathodic protection, yes, but mainly design issues is the way to handle, to mitigate those two types of corrosion. By design, I mean selection of metals, separation of metals. On the left, poor design, you've got, in the first one, you've got a aluminum rivet holding steel plates together. Where on your galvanic series are aluminum and steel? Aluminum is real anodic to steel. So you've got sacrificial anode holding your two plates together. So there's a design issue. Don't do something stupid like that. If you've got to have dissimilar metals together, do what they did on the right-hand side, separate them with dielectric materials. Just keep them separated. Here's another design issue, is how to handle corrosion, the two types of corrosion we talked about. This may be hard to see for some of you, but you're all familiar with this right out of ABYC's E11. This is how to wire a typical inboard DC system. Okay, you've got everything we're talking about. You've got a zinc, which hopefully they're going to start calling anodes instead of zincs, because we're seeing fewer and fewer zinc anodes all the time. You've got an anode here wired to your grounding bus, and your Cocks, your strainers, everything's chain plates, everything's tied in. Good bonding system like ABYC likes to see. Okay, so everything's tied together. Ground plate, anode, everything. Then you've got this wire going up to your DC main negative bus. Okay, everything's supposed to be tied together on a boat like this, right? Then we see this line here, AC grounding bus. Why do we have an AC grounding bus? There. For protection against electrocution or shocking, right? If there's any fault, ground fault, any place on this boat, since everything is tied together, that ground fault is going to go to your shore power system. It's going to go to your ground, okay? And not shock somebody on the boat. The fault is taken right off the boat through your AC grounding system, okay? But isn't that what caused our problem to begin with? Here's your AC grounding conductor right there, okay? That's what caused all the boats at the dock to be protected by your zinc over here. But that's the way it's supposed to be wired. It's safe from a personal safety standpoint, it's safe. From a corrosion mitigation standpoint, not real good. So what do we do? From a design standpoint, how do we handle that? We break the metallic path in the shore power system, okay? By installing a galvanic isolator. ABYC does recommend any boat that has a shore power system has a galvanic isolator, or an isolation transformer will do the same thing. This breaks that metallic path. Remember anode, anode, cathode, electrolyte, metallic path. The galvanic isolator on your boat gets installed right there, and it breaks the metallic path. So you can't have galvanic corrosion issues between boats now. What is it? How does it do it? And what does a galvanic isolator do? It stops the galvanic voltages from flowing. It basically breaks, using diodes and capacitors, it breaks the metallic path. But it still allows fault voltage up to the full system voltage to flow if something shorts. If your water heater shorts to the case of the water heater and you get a dead short, it still will conduct that short, that power, that current off the boat and protect the people on the boat. So you still have the capability, the safety aspect of your shore power grounding conductor, but you've prevented it, that same conductor, from conducting those galvanic currents. Paints and coatings don't do much to protect you against straight current corrosion or regular galvanic corrosion. Things to remember with coatings, though, is always follow the manufacturer's recommendations to the letter. I can't tell you how many surveys I've seen where the coating fights between owners and yards where they didn't follow the directions on the can. And also, don't ever mix products between manufacturers. If you don't do it right, this is what you end up with. You've got a break in the coating around these fasteners, let moisture in there, and the coating has now failed. So if you're going to use coatings, coatings are a very effective way to prevent corrosion. You've got to do it right, do it carefully. Here's another issue kind of tied into that last slide. It's similar to the one we showed before. You've got an aluminum rivet in a stainless plate, anode, cathode. Now, if that cathode is painted, let's talk about this one. If the reverse, you've got a stainless rivet in the aluminum plate. Aluminum is anodic to stainless, it'll get eaten up. But if you've got a good coating on that plate, it will be protected. They're isolated, okay? You don't have the electrolyte between the two, immersing the two, if you've got a coating on the anodic material. So coatings can be a way to protect against cathodic corrosion. Another way to protect against cathodic corrosion, sacrificial anodes, we've already talked about, impressed current corrosion prevention systems, and then bonding systems. Sacrificial anodes, this I believe is right out of ABYC, E2. Remember I said we're seeing more and more aluminum anodes? We, in this area, have to deal with salt water and brackish water, right? Not much fresh water on the bay, but it is certainly brackish. Aluminum anodes are the only ones that are really good for all three. Zinc's great in salt water, aluminum's great in salt water, aluminum's good in salt, brackish, and fresh. You won't see any magnesium anodes around here. We don't have fresh water unless you're in a lake. Yes, okay. Moving right along. There's a sacrificial anode. Think that one's doing any good? It's painted over and it's eaten away. It's not doing any good. here's the same slide we had before. Notice one thing, ABYC talks about placement of anodes. Don't put it right behind the propeller. Tuck it up out of the way, out of the propeller wash, okay? Impressed current systems, it's just like a conventional cathodic protection system, only it's being driven by a controller that provides the current. If you do have used an impressed current cathodic protection system, you have to, and it's normally on a metal hull, you have to protect the hull around the anode from the electrical current around the anode. So you'll see a dielectric shield. Here's the most common ICCP system is the Mercathode system. Bonding system, here's a nice bonding system, green wires, everything's tied together. You can see one bonding wire comes down to a shaft brush. Think that bonding system's doing any good? No, corrosion. Perfect. Yeah. And what's wrong with this one? You see something wrong with this? Couple probably zincs, or at least anodes on the transom of a boat. One's eaten up, one's pretty nice.
Wires are broken.
Think a bonding wire has broken off of this one. It's just sitting there. The other thing to keep in mind is that white coating on zinc anodes is zinc oxide, and it effectively insulates the anode from the zinc from the electrolyte, so it won't be doing any good. So if you haul a boat out and you see a lot of white crusty stuff on the zinc, knock it off, because it's preventing the anode from doing what you want it to do. Okay, ABYC has 4 standards that deal with this. E2 tells you everything you want to know about cathodic protection. It tells you what you're looking for. You're looking for a 200 millivolt shift. We'll talk about a little bit more about that in a minute. Anode placement, bonding its conductors, what to use, what not to use, how to connect them. Talks about aluminum drive units, aluminum hulls, steel hulls. E2 is everything you want to know about cathodic protection. Now, a corrosion survey. What's an indication of why somebody would need a corrosion survey? Rapid anode consumption, obvious signs of metal deterioration or coloring, haloing around the antifouling paint around the protected metals. That means you got probably have too much protection. Tools for the survey, multimeter. Everybody's got one of those. Amp clamp, I think that's the one I've got. With a diode test function, because you want to be able to test your galvanic isolator to be sure it's working. Silver chloride reference cell, inductive AC probe, we've all got those. Split cord, it's just a shore power cord where the 3 wires are separated so that you can test them individually. On and on. Randy's giving me the evil eye over there. I got to move on. Corrosion surveys. You've got to be thorough and systematic. And the first thing to do with a corrosion survey is gather data, because quite often that will tell you where to start looking. Timeline. Did something happen real fast? It's probably stray current corrosion. About the boat. Did the owner just have some more equipment installed? Is there a galvanic isolator? Isolation transformer, polarization transformer. Has he installed some new equipment on the boat? Done any maintenance? How about new anti-fouling paint? Shore power issues. Ask questions. Did they just rewire the dock? Is the use of the shore power system changed? And then the use of by the owner, is the owner using the boat more? Is he using it less? Environmental changes, like, is it a really dry season? So we've got we got more salt water, which is a stronger electrolyte. Then when it comes to the tests, first, these are the ones, this is a process I use, my checklist. This is an old one, and I have made some changes, some minor changes to it. But I always start at the dock. Is the dock pedestal and the dock system wired properly? Check the polarity, check the grounding. Interesting question. What if you check and you find that there's a serious ground leak on the shore power pedestal? What do? You tell the marina owner? Yeah, you probably should. What you should tell him is that he needs to get it checked by his electrician. But this is a test of the shore power system. Then you want to check the grounding system on the boat. Is the grounding system proper? Do you have continuity between everything you need between your grounding conductor on shore and your the main the engine block or main negative bus? Is your grounding system working? Then start checking for galvanic currents and stray currents. Here's checking for the galvanic currents. Shore power's not connected, first of all. Then you take off your bonding, the wire to your zinc, your hull zinc. This assumes the boat's in the water. You take off the connector to your zinc and then test between your reference cell dangling in the water and your engine negative bus, and that will tell you what the hull potential of the boat is, okay, without your transom zinc installed. Now keep in mind, you may still have a shaft zinc or rudder zinc or something, which can affect your readings. But your first thing to do is determine what the hull potential is. Then you reconnect the bond wire and test it again. The voltage between your reference cell and your engine negative bus, DC negative bus, you should see that 200 millivolt negative shift. That tells you your boat's bonded properly. You've got enough anode in the water to give you a 200 millivolt negative shift. And then if you don't get it, I've got the test and the criteria right in here. Should be a 200 millivolt negative shift. If it's less, this is what you got. If it's more, this is what you got. Here's where you check for stray current corrosion issues. Boat's not plugged in, and turn off all your breakers, and then check. Where are we? Not plugged in. This tells you that you shouldn't see any voltage change in this step. As you turn each breaker on, AC and DC breaker on individually, checking between the voltage between your cell and your engine block or main DC main negative bus. If you see when you turn a breaker on, like your bilge pump, and you see more than about a 10 millivolt jump, if you see a significant voltage jump, chances are then that piece of equipment that you just turned on is the problem, is causing your stray current. The whole key here, though, is be systematic and record everything so that at the end of the day, when you spent the whole day in the bilge of this boat trying to figure out what's going on, and you go back home to your office and you're studying it, trying to figure out what's going on, you've got the data written down so that you don't have to go back to the boat and do some more research. Okay, be systematic, be thorough, and write everything down is the best way to figure out what's going on. I always figure a second trip back to the boat if I'm doing a corrosion survey. The first trip, gather all the data, go back to the office, spend the evening trying to figure out what's going on, come up with a hypothesis, think I found it, go back to the boat and test it out. Quite often I'll also have to go back to the boat and get some more data because there's so much data. This I showed you like 4 pages. My corrosion survey sheet is like 8 pages long. It's a lot of data. Sometimes you get lucky and find an obvious problem, but more often than not, it's not a single obvious problem. All right, that was real fast. Questions? Yeah.
Those, that process, was that in ABYC? You had 3.3, 3.2?
No, that's my own, and it's a compilation of ABYC, these textbooks, Nigel Calder's books. Nigel Calder's probably one of the better, his boat owner's manual, is that what that big black book is called, a boat owner's manual or something? He's probably got the most thorough step-by-step process for this, and that's where probably most of this came from. But basically, it's just my evolution over years of finding what didn't work.
Can we have that presentation?
I think Randy's, this is being recorded.
Okay,
it's available.
so he has,
Keep in mind, these are fairly old, because this is a 150 slide, 2-hour presentation that I just chopped up.
Right.
So a lot of this stuff has been taken kind of out of context, and those slides are kind of old, so don't take them verbatim. Yes?
Will that information include your form? Things to check?
No, it's just these.
Could we get that from you?
I'll give you my card and yeah. Okay, any other questions, comments?
I wouldn't vote.
Yes, okay.
And you got electrification.
Yeah.
Do you use the same procedures or?
Yes. Chances
Bonding.
are you'll find, now, wooden boat is one place where I would consider not bonding. If you do a detailed analysis, you will probably find, if you're getting fuzzy wood and wood burning, you're probably going to find that you're overprotected. The shift that you want to see on a fiberglass boat, you want to see a 200 millivolt shift from hull potential to protected potential. On a wooden boat, because of the issue of delignification, you want to see a 50 millivolt shift. And that's such a small window that if you put zincs on and you test it and you got a 50 millivolt shift, within what, a month or two, those zincs are being eaten up, you've lost your 50 millivolt shift. Now all of a sudden you're out of the acceptable range. If you put too much on to begin with, you're overprotecting and you're eating up your wood fibers. The best way to protect a wooden hull is an impressed current system, because you can set that. You got to monitor an adjustable setting on that you can set it to maintain exactly the shift that you want, and that's usually about 50 millivolts. Anything else? Okay. Great. Thank you. Oh, thank you very much.